Alright, so I'm going to be solving LeetCode 1631 medium in C++, as always. Path with minimum effort. So effectively, you're a hiker, right? And you're given this grid of spots. You're trying to get from top left to bottom right cell in the grid. And each cell in the grid represents the height of that specific region. You want to find a path to get from top left to bottom right that requires the least effort. How do you quantify effort in this case? Well, effort is quantified as the difference, absolute difference, by the way, between two heights, horizontally or vertically adjacent to your current height. So in this case, the effort between this cell and this cell is 1 because you have climbed a height of 1. You then want to find out, okay, what's the minimum higher path effort in this path? In this case, it's this one. Why? Because okay, I have climbed. You want to find out the minimum effort expended overall. Minimum effort expended overall will be the maximum effort that you expend over the course of one path. So in this case, your effort between here and here is 2 because you've climbed up 2 units. You then climb up another 2 units, so it's still the same level. You've expended no more than 2 over the course of your path. You then go down here and then go up by another 2. But it's absolutely different, so going up and down, it doesn't discriminate. So you're still expending 2 effort to go down this hill as well, and going to go up. Overall, this is the lowest path. Why? Because if you go down this path, for instance, you have 1 to 2, so you've climbed up 1. Your maximum effort over the path is now 1. 0 because you've not climbed, 0 because you've not climbed, so your maximum effort over the path is still 1 that you did to start with. Then it's 3 because you've climbed up 2 to 5. So your maximum effort over this whole path is 3. It's not the minimum effort. So you're seeing this graph matrix, but you can kind of consider this a graph in this context. You see a single source, you're trying to get from one to the other, and you have costs or weights. If you've studied data structures and algorithms at any university in a computer science or electronic engineering computer science degree, then what immediately comes to mind and what should come to mind is Dijkstra's algorithm, or any sort of single source minimum algorithm that involves costs. I say Dijkstra's here and not something like Bellman Ford or Floyd Weichel or whatever, because it's number one, the go-to algorithm for this case. Number two, we know it works because we have all positive weights, and Dijkstra's algorithm will guarantee us the shortest cost over a path from a single source if all of the nodes have positive weights. So we know that we can do this. It actually makes things a bit easier because unlike in other graphs where the endpoint is a little bit ambiguous, and you have to track visited modules in a more niche way, and it's difficult to know where you end, here it's very obvious where we end. We end when we get to this node. Now, we're going to have to use some sort of heap or priority queue because that's what underpins the whole algorithm. And it should look very straightforward, but otherwise I will explain as we go along. So firstly, let's think, what do we have to track? Obviously, let's think we have to track, we should store tuples, or some sort of vector in this case of integers. 3 integers are essential for conducting this Dijkstra's algorithm search. 1, our effort so far. Now, what do I mean by effort so far? Like I said before, what was the maximum effort we have expended over the course of one path? Right, for instance, our maximum effort in this path, 1, because we've gone from 1 to 2. It's still 1 because we haven't done an effort higher than 1 yet. Still 1, now it's 3. So our effort so far means the effort since the starting node. What was the maximum effort we expended? And then obviously we want to track things like our row and our column so that we know where to go from given our current position. Okay. What we also want to do is be able to track where we visited. This means that, let's say I'm here, right? I'm at 8 to 2, right? But, I've gone through this path, right? And I look at this path, I'm like, oh, maybe I want to go up. But what if we've already found a cheaper way to get to this path? For instance, we could have just gone right instead. This way it avoids us recalculating the same things, because we only want to store something, using the whole edge relaxation concept, we only really want to store something when we found an even more efficient means of getting to that node. What I mean by that is, why bother going from 8 to 2 if we already know that we can go from 1 to 2, which is less effort, getting to the same point? It's pointless, so we should just skip it altogether. So we should obviously track the cheapest effort that it takes to get to a given node. That way we can track what we visited, and we know not to do unnecessary computations. Okay, so with that out of the way, let's code it all up. So first things first, I want to get my bounds in mind, because obviously we're going to be doing matrix traversal, so we don't want to go out of bounds, given our directions. In fact, let's do our directions first. So let's have a vector of pairs called directions, which will contain, we can go up, we can go down, we can go left, and we can go right. Those are our 4 directions. It's 4 directionally adjacent. We also want to have our bounds, like I said, so we want to have int rmax, which is going to be our maximum number of rows, which will be the size of the matrix, and then we want to go columns max, which is going to be the size of 1 row. There we go. We also want to instantiate a vector, another matrix called visited, which we will instantiate with this many rows, and we will have each row containing C max number of rows, and all of those will be initiated to infinity. That's because in Dijkstra's algorithm we say that any node that we've not visited is infinity. That way we can easily track, like at the start, is it lower, and and so on and so forth. So that's out of the way. We then want to have our priority queue, and our priority queue takes into account, we store vectors. Obviously we store 3 element tuples, or vectors in this case. We store vectors, and we want to make sure that it's initialized as a min heap, so use the C standard for this one. I always have to make sure I get the right number of less thans or greater thans in this case, because I always mess it up. So PQ. Now we also want to store in visited 0, 0, which is going to be equal to 0. Why? Because at the start it takes 0 effort to get here. We're going to presume that we were already here to start with, so don't bother. And we also want to push in our first value. So our effort so far to get from 0 to 0 is 0. The row is 0 and the column is 0. So while our priority queue is not empty, what are we going to do? So firstly, we need to see what's our current position and what was the effort that it took us to get here. So to do that, we want to get the top element of the min heap. Now, the min heap is great because the top element will always be, the way we've instantiated it, the top element will always be the path that we found so far that has the lowest overall effort from the start. So we'll get a vector of integers called current position, which is going to be equal to the top of the priority queue, and then we want to pop off the top. We then want to get our values, so int we're going to have an integer called effort so far, which is going to be equal to the first element, because that's the way that we've structured this. So it's going to be equal to current position 0, and then we're going to have int current row, which is going to be equal to current position 1. And we're going to have an integer called current column, which is going to be equal to current position 2. Now, this is great. Firstly, we want to have an endpoint, right? So eventually we're going to pop off an efficient, like our most optimized path. If we've popped off the top and our current row and our current column are this point here, then we know that we've gotten to the end, right? We found a path. This is the cheapest path to get to this point. So we can end at that point. So if current row is equal to R max minus 1 and current column is equal to C max minus 1, then let's just give back the effort so far. So return effort so far. This is the effort over the whole path. That's where we're done. Otherwise, if on the other hand, if we've come to a position that we've already come to, like for instance this example here, right? For instance, we've come to this node 2 and we've already visited it, and we visited it with a cheaper effort, that we don't want to bother with the rest of this iteration. We're not interested. So if the visited value of current row, current column is in fact less than our effort so far, so we've come to a point where we've actually already come to with a cheaper effort, then we don't want to bother. We just want to skip this iteration. Otherwise, we have something juicy. So we're going to do a range-based loop here. We're going to go through all the possible directions, right? We're going to add, let's say we're at this point here, we're going to check left, we're going to check right, we're going to check up and down. We're going to see, okay, do we have a potential spot which has a cheap effort? So we're going to have ints difference in row, which is going to be equal to directions first. We're going to have an integer difference in column, which is directions second. We then want to see, we want to do get our new row, which is going to be equal to current row plus the difference, and our new column, same thing. Obviously, first we want to check if they're in bounds. So if new row is greater than, if new row is greater than R max minus 1, or new row is less than 0. Alternatively, if our column is greater than column max minus 1, because obviously it's 0 indexed, or our column is less than 0, then we're out of bounds and we don't want to bother, because then we'll get an overflow error. Otherwise, we have a valid position. So we check, we get the integer maximum effort, which is our effort now, which is going to be equal to, so let's say we've come to this point, our effort now is 1. We've now come to this point, right? The height difference is 0, but we've still covered 1 overall effort, right? That's our maximum effort. So we're going to take the maximum between, if the height is greater than, if the height difference is greater than our effort so far, then our effort so far overall is higher, because that's the most effort we've expended over the course of the path. For instance, at this point here, we've expended 2 effort, then we go right. We've now expended a maximum of 5 effort, because our largest difference has been 5. So we're going to take the maximum at any point between the effort so far versus the absolute value of the difference between our new row and new column minus the old row and old column. Now, if we've actually, so if visited new row, new column is actually greater than our current effort, so let's say we've now reached a point, we've come to the same spot, but we've come here with a cheaper cost, then we want to update that value, because obviously now we've found a cheaper way, we've done the edge relaxation, we found an easier way to get to that same spot, so we want to update the value. We then want to push in, we then want to push in our we want to push in the effort now, the new row and the new column, because now we've found a new possible path extension in our frontier with a more optimal path. And eventually we're going to get to the end and it will return that current path. If we break out of this priority queue without actually returning anything, then we know that, well, I mean, it's not really possible in this case, because you're always going to get to the end somehow. It may not necessarily be the best, but you know, you will find a way to get to the end. You have to return -1. So let's see. Remember the directions go first. My bad. Yeah. Have to watch out for these things. Run and code. Heights. Run the code. Submit. There we go.